Good day. I'm going to be talking about classification using nearest neighbors, and my agenda is very clear. I'm going to walk through what a scenario around which where we see the need of having K classification. What is K classification? I'm going to run some demos specifically around Azure machine learning and what are the things which one can achieve and cannot achieve in Azure ML from a K classification standpoint of view. And then I'm going to walk through certain demos around the R object model. So I may kind of start with talking on the demo side of the R object model, and then I'm going to talk in terms of where you're really going to be using K classification. And the last, I'm going to be leaving everybody on a note in terms of the K SWOT. So without further delay, I'm going to get into a scenario where it's a classical place. We eat a lot of food, and the food has certain taste. It's got certain crunchy factor, and so we kind of go ahead and build a graph in terms of how crunchy the food is, how sweet the food tastes, and based on that, we just come up with this rough graph where we actually talk about lettuce, celery, and green being all kind of enclosed to one another, and carrots, so on, so depending on the crunchiness factor and the sweetness. And similarly, you see on the right hand side, you see a lot of the sweetness where you see apple, pear, grape, banana, orange, which are high on the sweet factor. Apple's kind of crunchy up there, and plus it's sweet, so that's the reason it's up right in the corner. And on the lower right, on the lower left, you see a lot of food items which are cheese, shrimp, bacon, nuts, fish, which are relatively soft, and they're not sweet, so they kind of fall into that category. So as we kind of start plotting the data, we start seeing certain amount of boundaries getting formed, and these boundaries, what eventually we kind of classify them as fruits or vegetables or proteins. And so let's take an example where I need to go ahead and predict something new which is coming, and I need to go ahead and say where exactly it basically lies. So I see tomato. I mean, tomato is one part of the problem where we've really not got a very sure answer. And what really, based on the sweetness of tomato and the crunchiness of tomato, we kind of see it's somewhere between the fruit and vegetable. And what lines you see in terms of the tomato to a green bean and tomato to a grape and tomato to nuts and tomato to orange, that distance is called Euclidean distance in the scientific world. And I'll get to a minute in terms of what. So the whole problem solving of classification by trying to group all the data items which is similar in nature based on their features is something what we do some kind of classification. It's called clustering. So we kind of put all the data in terms of clusters, and then we the clusters, depending how well formed they are, any new item which kind of comes up, we are at a point of basically predicting in terms of what cluster it falls, and hence we can tell what is a tomato or what is not a tomato. Okay, so going some definitions. So KNN, so this classification which I just talked about is KNN, which is a principle to classify data by placing it in the category with the most similar or the nearest neighbor, like you saw in the earlier example. The Euclidean distance, which is the distance one would measure if you could use a ruler to connect 2 points, illustrated in the previous figure by dotted lines connecting the tomato to its nearest neighbor. And K is more relevant to the syntax. So K is the minimum number of distances with the nearest neighbor to classify the data. So how many nearest number of distances would I basically say if I find, let's say for example, I may get something else here which is very close to tomato, and based on those three things, then I may define tomato or fruit. Similarly, if I get something better, so which of the distances, nearest three neighbors out here and the nearest three neighbors out there, which one we kind of course in the case of tomato we may or may not have the K nearest three distances. Now from a syntax standpoint of view, I have predominantly been using R and R out here. So basically, we see KNN set is the basically the set where it's going to get the data into. So KNN is the algorithm. You need a training set like we initially talked about in the example, the scenario example. You need a testing set, and you obviously need the labels of training set in terms of identifying what I really want to do my classification again. So here, if I go back to this example, the labels ideally would be fruit, vegetables, and proteins. And K is equal to 3, where I actually goes in the minimum number of distances with the nearest neighborhood to classify data, which I can conclude that this data actually, in the new data which is coming, can be classified into any one of the scenarios. Now, I'm going to get into the demo with the R scenario. Okay, so here I have my R scenario. So the example that I'm going to run is basically a wells. So it's specifically in case of oil and gas, and oil and gas, as you know, upstream, they have go through the initial process of oil exploration, and then eventually they build wells, and those wells, they have a lot of data in terms of what's the depth to be totally measured, there are a lot of financial values associated with the wells in terms of the production volumes, which is the most important, and if the well is going to be a turnaround candidate or no, and the volume variance. So we, in the business world, from an oil and gas standpoint of view, the health of these wells is something which everybody is kind of concerned. And well, getting into detail into the example, so this is the data set we're dealing with, and it's about 11,223 observations with 27 variables. And what we are going to be doing out here is we are obviously, the first and foremost is we need to be very careful in terms of classification or any kind of machine learning algorithm which we run. We need to make sure the data is good and clean. And if the data is not good and clean, probably you'll never be getting around to run your algorithms right, and you may not even get the right results. So here is the syntax where I actually just go and all the null and NaN values which actually come when I actually import the data is I'm kind of setting it up to zeros, because that's so this becomes my training set, which is about 1 to 9,000. So I'm just going to kind of put this as a training set. Similarly, this becomes my testing set. Okay, now these are my labels of the training set. Okay. Similarly, I may have the labels of my testing set. Sorry for that. And here I go ahead and finally run my algorithm, run KNN with all those parameters. So I actually talked about the testing set, which is my training set, my test set, the labels, and K is equal to 3, which you actually mentioned. Now, apparently, let's go run this. And obviously, I'm going to run this. Sorry for that. And the parameter which I classify my data on is the first parameter, the business unit. So that may not make sense, I don't know. So it's something which it's just classification where the next data which is really going to come, which business unit is this well really going to lie in. Or probably on a better case, I may take something different. I may take 26, which is is this well a performance? It's a turnover candidate or not. So let's get on to the cycle and run this algo. Sorry for that. Okay, so all right. So I'm sorry for this. It doesn't. These are the. Just for the explanation standpoint of view, I kind of put this, which doesn't get there. So my apologies for this. And so here I am up, and I will go ahead and run this same stuff again. And here I go, and let's see how it actually comes out. Okay, so here is my data. So 78 is idly. So one thing is that most of the algos within machine learning do not understand or do not want to basically spend the time understanding the alphanumeric data. And so 78 and 89 are values which are replaced for a yes and no. And so if I'm looking at the data set which I've got, and continuing with the part two of this. So if I'm looking at the data set which I've got, and here's my data set and the initial data set, let me talk about the training data set, which is about 9,000 observation, and I need to, so I've kind of replaced this yes and no with the 78 and 89. So 78 refers to, this is a no, and 89 refers to a yes. And the data set which I have is split into a small and a test data set. Now this is the test data set where which we run our assumption against. So the small data set is where we actually run the KNN algorithm from a training standpoint. After we manage to get the training set on that, the next thing we actually do a cross tab to basically figure out the prediction which actually comes out of it based on my new training set, on my new testing set, what is the correlate. So I had about 2,202 records in my testing set and about 9,000 records in my training set. After the training, I've managed to build the response made, from KNN set. And in a minute, let me just show what KNN response really looks like. So it talks about 78 and 79. It's taking the 2002 odd. And now, but I need to kind of look at if my data, which is in my testing set, and the relevance of the result set, which is coming in KW set 1, which is the response from the KNN clustering based on. So I want to see what's the differential. And so I got about 2,202 records in my testing set. And I've done a cross tab across my test labels and the output of the KNN. And here what I've done, so if you look at the matrix, this is the test label, this is the KW set, and we do 78 on 78. So basically a no unknown prediction. So what the algo predicted as a new test data, which is going to be a no, and it was about 1985, which is 1985 of the records are going to be a no, 36 of them are going to be yes, and roughly if I'm looking at if I'm looking at a total of 2002, there's approximately close to about 2,000 records which are in line with the prediction of the new data set. So our prediction algorithm is running at what rate? Let's probably take a look. So if I'm looking at about 1986, 1985 plus 36 divided by 2202, that's about doing a 91.7% 91.7% prediction rate is quite correct. And the remaining stuff where we actually see a 78 on 89, which is close to about 68, and an 89 on 78, which is about 113. These are something which are false positive. So if I'm looking at this and this, these are false. So these are the the real values, real positive values. This is the false positive value. So we can deduct that about 91.7% of the times this data set and this algorithm will be in a position to classify the data rightly. And of course there'll be about stray cases like tomatoes, which probably may not fall in either of them, which would actually be 68 and 139. So that's the case of tomato. And now I would want to kind of look at so that was a demonstration with R. Now I'm going to go into the next part as a demonstration with Windows Azure. So we looked at, I mean, in terms of the model which we already talked, and we're going to be running the same stuff on the turnaround prediction on R. We actually talked about, it's got two execute R script. One is basically just in terms to basically get the packages which installed on R. Ultimately, everything within machine learning internally runs on R. So that's how you get a sense in terms of a lot of R which is happening below the hoods. Now, what I've done out here is simply taken a cut and paste of the what's available out here in my R Studio and just gone ahead and put it out here. And let's run this and let's see in terms of how what's the kind of output I get. And the reason I want to kind of do this is basically kind of give you a sense in terms of what would be out of box in terms of Azure ML versus what would you really need would one really need to do in case of a real life scenario. Now, first, let's take a look in terms of what are the packages which are installed on Azure ML from an R perspective. And so we can see a whole lot of packages. I mean, you can come back and go back and later take a look at this entire stuff. Next, I want to basically take a look in terms of what's my output. Now, the output which I get, oh, it's fine, it looks good, but it doesn't give me the insights in terms of what I really want to look. What I really want to look is this. This is exactly what I would want to be playing around with, is basically getting to know in terms of how my algorithm is performing, what is my crosstab report specifically in terms of the mixes and matches. And this is exactly what it gives me. I mean, I don't think probably I would get this kind of output from typically from from the Azure ML standard construct, and hence I went ahead and used execute R. Now, getting back into now, where do we use KNN? It's pretty straightforward in terms of where do we use KNN. It's basically from a classification standpoint of view. There's not much of relationship, and the data is very complex, and trying to establish a relationship is fairly difficult. Now, getting into the SWOT, the last line which I have, strength, simple, effective. Make no assumption of the underlying data distribution. It really doesn't give a model out. So fast training phase. Weaknesses: does not produce a model. Slow classification phase, requires a large amount of memory, and nominal features missing out. Missing data requires additional processing. So this is where KNN is. Now, just to let you know, while before I kind of get off or basically leave this presentation, I want you to guys to know that KNN is a very powerful algorithm in terms of clustering. So most of your big data projects which initially does come out do start up. I mean, you're going to start up with clustering or classification of the data, and does really help you set your direction right. So please do use KNN as your starting tool, and thank you for watching my presentation.